Okay, just a little detail about allylic bromination we have to talk about. From previous video, we did this together, right? So we do bromination on this compound. Bromine, the bromine will form radical right here at the allylic position, not at tertiary because it's got a resonance stabilized and more stable, blah, 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 right? It's also actually because of the CH bond right here is the weakest bond among other CH bond in this molecule. If you look at the structure of regular alkene, the weakest CH bond is at allylic position. This only takes 365 kilojoule per mole to break this CH bond, allylic position. Not like vinylic 444. The radical right here is not stable. A regular, so this is secondary alkene and not alkane is not stable. Allylic got radical got resonance stabilized to the more stable, the easiest to break. So basically, you can do the radical bromination right here. All right, but we have a little problem with this reaction. All right, so this is like practically, this is what happened. We're going to set up this reaction. Put alkene into the flask as a solution, add this bromine solution into the flask, let it sit outside, have a sun or add heat into it until bromine forms radical. So you're going to get the radical chain reaction. So initiation, propagation, tons of them, tons of propagation, and tons of termination. That's why we call chain reaction. Anyway, so we have to add this, add that, and the light. But the process of making radical, it takes some time. Some of the bromine who hasn't touched light yet, and there are a lot of them, we add tons of bromine at the same time, right? Some of them going to do a radical. Others who hasn't touched light yet, going to go to do this reaction. Are you familiar with it? That's the bromination of an alkene. Bromine just got added onto the reaction, and this reaction doesn't need light. I label right here, no light needed. Okay, this is bromination of alkene. So that's a competition against radical bromination, which means that if we add too much bromine at the same time, some of them going to go to this route. We're not going to have a lot of product here. That's the biggest flaw of this reaction. Well, let's think about this real quick. So what's the problem? The problem is too many bromine cannot go radical bromination at the same time, right? We want it to go this way. Some of them just go do this. So how do we solve it? Well, can we add bromine, the small amount of bromine as over the course of reaction, not just like add tons of bromine at the same time. So to make sure that all the little bromine that we add to the reaction, each one of them go radical. And here's how we do it. So we're going to use this reagent. So N-bromosuccinamide or N-chlorosuccinamide, depends on you want to add bromine or chlorine. Okay. So the NBR and NCl bonds are weak. They are weak bonds. They can easily be broken by add light or heat. So we're going to use this reagent and the light to generate bromine radical over the course of reaction. Not just like add bromine at the same time. We keep adding. It's automatically adding bromine to the reaction, feed the reaction with the bromine radical. Here's how we do it, right? At initiation, so we have N-bromosuccinamide, add heat into it or light. So you will get bromine radical. And this reaction takes time. It happens over time, right? Not just like bam, right away, happen right away. So the bromine radical will be produced over time and not enough to just add it to the pi bond. And this is not the molecular bromine either. It's just a radical. So, all right. So, and then this guy will go to propagation and everything else the same thing. So hydrogen abstraction, you get a radical there. And then this guy will go attack so this is propagation, radical attack, non-radical. If you were to add a bromine, this is going to be molecular bromine, right? But we don't have molecular bromine here. So the only source of bromine is just this, the N-bromosuccinamide. Here we go. Right, this is the chiral center, so you get two compounds there, and termination. All right, now you just pick the radical, attack radical. You can do the alkene and alkene radicals, bromine radical. You can do succinamide, or you can mix all this up. Fine. Oh, mix all this up. It's okay too. I don't really care about termination. All right, the propagation is where we care the most. All right, if you do this reaction, first off, where do you get radical? Don't think about the product for now, right? Where do you form radical, first of all? This is for this NBS and light. This is for allylic bromination, right? So we go right here, in the middle right here. Say one more time. We don't add bromine, molecular bromine, to this reaction because if you add molecular bromine, there are too many bromines in the reaction. Some of them going to go to radical. Others going to go attack add bromine onto the pi bond. right? So we don't want that to happen. So we have to use the reagent that create or produce bromine radical over time, not just add them at the same time. So we use NBS and light. Okay, so we go to form a radical right here in the middle, right? But this radical is allylic position. They can form resonance. Sometimes you're gonna see that it resonance to form a radical on the other side. Not a lot for sure. This is primary radical compared to tertiary. Not a lot, right? So most of the time they spend on tertiary, and each one of these can form the products, all right? So you might get multiple products here if this radical is stable enough. Of course, the major product gonna be right here. This is good reaction, right? But sometimes I just give you kind of open your thinking box, right? You're not gonna have just a product here. You could have the resonant product as well, but is it a lot? Well, the stability probably not comparable to the tertiary. So there's a major product. It's gonna be minor or very minor, okay? But it's possible. Just give you the possibility. All right, we have this compound, NBS, carbon tetrachloride. That's a solvent, so don't have to worry about it. And add light. So where can you form the radical? First of all, you should see it. Initially, you should see two positions that can form radical. That one and that one. Both are allylic, right? And if I ask you which one's better, of course, this one's more stable. Okay, but now we have more radical. If you do resonance, there. You can form a radical right here. This is secondary, right? And we have another one is also secondary. Okay, tertiary is still the best. The tertiary will go from a lot of product with the N-bromosuccinamide to get this guy and enantiomers. This is the chiral center, right? This guy can also form the reaction as well. So you got a bromine right here and enantiomers. Oh, this is supposed to be hydrogen, guys. So watch out. This is hydrogen, not a methyl. All right, this is wrong. This is hydrogen here. Down here, what we got, so this radical, so you can form a bromine right here, and enantiomers, and the radical right here, and another enantiomers. Okay, so you should get 1, 2, 3, 4, 5, 6, 7, 8, possible 8 products. But of course, the major product is going to be this guy because the major radical, the most stable radical is right here. Okay, so I don't think that a lot of this will form, but I don't really know. I never done radical reactions, not really my focus on my graduate career. So, but this is a possibility. But the major one, still this guy. Okay, major product. All right, we have class activity number 3, question 1, 2, and 3. We got, and these are the keys.